Welcome everyone for the FDP on Advances in Materials for Engineering Applications. So today we have a day 5 session which precedes the past discussions of various scientists who discussed on about like FEM, the material advancements and the composites, polymers and the design of polymers and testing of polymers. So in preceding to that, yesterday we had a session with Dr. Sechvasan Reddy garu, and he was like discussing about the main concepts of acoustic metamaterials. So in continuous to that, I have an interesting application. So one of its most applications the materials are in today's trend are going with, which is nothing but aerospace engineering. So let us start with it. Before going to further discussion about it, I just wanted to give a brief about like what aerospace engineering is all about. So coming to a complete guide to aerospace engineering, whether you have just graduated with a degree in aerospace engineering or you're considering becoming an aerospace engineer in the future, these tips will help you decide whether aerospace engineering is right for you or not. So coming to the aerospace engineering, it is a process of designing, creating, building, and manufacturing anything that flies, jets, helicopters, and even spaceships are all part of this field. The two main branches of aerospace engineering are aeronautical and astronautical engineering. The former deals with any craft that flies within the Earth's atmosphere, or the later deals with anything that flies outside the atmosphere. So the next one, like what do astronautical engineers do in real time? So astronautical engineers build an aircraft that can fly within the Earth's atmosphere, including military flying technology, commercial and passenger jets, helicopters, and even drones. And many people feel that aerospace engineers only come in to be in the part of 20th century, but scientists and dreamers have been designing missions to fly since the Renaissance and beyond. So what do astronautical engineers really do? So astronautical engineers design and build spacecrafts. They have to deal with all the complexities of the harsh outer space environment. The field is engineering. It is a field of engineering. Is quite literally a rocket science. It is the field that requires a lot of intelligence and attention to detail. Hence, why would people joke about comparatively simply saying that hey, it's not rocket science. So what is the difference between aeronautical engineering and aerospace engineering? And there isn't too much of a difference per se between aeronautical and aerospace engineering. Aeronautical engineers is more of a subset of aerospace engineering, and aeronautical engineers focus more on building aircraft that fly within the Earth's atmosphere. They get an education in the basis of math, physics, and chemistry with more advanced studies in propulsion, aerodynamics, sensors, power generation, and the other scientific topics. Both general aerospace engineers and astronautical or aeronautical engineers study these topics. But aerospace engineers may work on the spacecraft that goes outside the Earth's atmosphere in the field known as astronautical engineering. So what is the difference between aerospace engineering and astronautical engineering? While aerospace engineers study the aforementioned topics, astronautical engineers have an additional task. They must build and design spacecrafts that function both within the Earth's atmosphere and outside of it. This includes the topic like thermodynamics and quantum physics at the bachelor's level, and things like space navigation, rocket propulsion, and orbital mechanics at a graduation level. What does aerospace really mean? The word aerospace is like a relatively new one, as it was first used in 1950s. The meaning of the word is anything pertaining to the Earth's atmosphere and our outer space. So it is a compression basic Greek words as air and atmosphere or gases. So you may recognize it from few other words dealing with these topics like aerosol and anaerobic. Space was first used in relation to outer space in the late 1800s. However, it has been used to mean an interval of distance since 1400s. So in this case, like it may refer both. What does aeronautical really mean? The word aeronautical means anything related to building or flying aircraft within the Earth's atmosphere. It was first used in 1780s in relation to the Burgyang aircraft of the era, like hot air balloons. What does astronautical mean? Astronautical relates to building and flying of aircraft that are meant to go into outer space. It contains the word for the scientists and travelers who pilot and live on these spacecrafts, like astronaut. The term was first used in 1920s when the field of space travel became a possibility and interesting in society. It is also like a Greek abstract word. that has been designed. And coming to the technology, what is aerospace technology? Aerospace technology is a broad field of since planes, spacecrafts, and other flying objects have so many components to them in modern times. It includes everything from propulsion systems to airplane wings and helicopter blades. However, it is more than just the mechanics involved in flying. It also includes things like security, operational software that pilots use to make airborne vehicles work. Think of in detail that goes into an aircraft. That's aerospace technology. So what is a rocket scientist? Technically speaking, a rocket scientist isn't an official position. NASA, the National Aeronautics and Space Administration, says there are rocket engineers and scientists, but there isn't necessarily one position that combines the two disciplines. However, rocket engineers and scientists may work together on aerospace projects. Rocket scientists may be thought of as people who work on propulsion systems for aerospace projects, or anyone who works in the aerospace field. How do you become one? Well, since it is a synonym with an aerospace engineer, the path is very similar. Just to get a degree in the topic, and you might consider telling people you are a rocket scientist. And coming to the more about aerospace engineering, the first thing that comes in mind is like Abbas IBN Furness. So he's the first aerospace engineers in history, and I believe like Jean Francois, and there are many more like Sir George Kelly. So who are the first inventors? So what is like NASA is really dealing with aerospace engineering. As I told you, NASA stands for National Aeronautics and Space Administration. In the US, the government bureau is responsible for aerospace research and national space exploration programs. Some of the best aerospace engineers in the country work at the agency, and many who study in the subject list working for NASA as a goal. What types of aero engineers jobs are available at NASA? Well, you could be an astronaut, a mathematician, a quality control inspector, a technical communicationist, and many other roles. And both missions have aerospace engineers working together towards very different outcomes. The ISS is a space station where astronauts from different countries work together to make important discoveries about the difference between life on Earth and life on space. We have seen like recent movies, Life, and there are many other movies like which illustrates the similar concepts of these, which makes you feel so much interesting about these space studies. And the Curiosity rover is a mission that was sent to the red planet to determine whether or not life has ever been possible there. Of course, other space programs in the past have gained international acclaim, including the Apollo missions and the Hubble telescope. So aerospace engineers made all these projects really possible in time. And coming to the aerospace engineering and space tourism or travel, most futurists agree that space tourism is going to be the future of aerospace engineering. Although scientific research and exploration of the solar system will not stop. At the moment, Richard Branson's company, Virgin Galactic, is on the forefront in the burgeoning field. In May of 2018, I believe, the company's spacecraft, the USS Unity, had its second successful launch, causing Branson to state that he expected to go into space himself within a year. And similar to that, right behind Virgin is Amazon CEO Jeff Bezos' company Blue Origin, which has excuse me, had successful launches in recent months. The company plans to set up a base on the moon and may work in conjunction with NASA to do so. The field of aerospace engineering will explain in the future to include space tourism and travel, and many more engineers will be needed to fuel this growth. And coming to the industry concept, like what does this aerospace industry is really about? Is very intriguing and exciting, especially in your modern era. It attracts people with the scientific and mathematical knowledge, those with a curiosity for what makes things go up, and those with a desire to improve on current technology. As an aerospace engineer, you can expect to work for a company in the tech, defense, or aircraft or space industry, or for the federal government. The industry itself is very dynamic, and many engineers find a position that suits their interests while offering plenty of opportunities for advancement. And similarly, like what this particular aerospace engineering and the tech industry is all about is engineering has a lot of crossover with the tech industry, as most of the modern aerospace startups, including Elon Musk's SpaceX, I believe, and Blue Origin, Virgin Galactic, as I told you earlier, are headed by CEOs who are also adept in technology. As consumers become more involved in air and space travel, so consumer technology will become even more important in conjunction with aerospace engineering. And these firms require tech-centered positions like software developers, IT professionals, and consultants familiar with the unique data, heavily and speedy processing requirements of the aerospace industry. And coming to the aerospace engineering with the space industry is seamlessly tied to aerospace engineering. Engineering, engineers, are needed to safely get people and supplies to space, and more importantly, back to planet Earth. And the potential jobs within the space industry for aerospace engineers include launch engineer, antenna engineer, and safety and training specialist. So there are various other positions. And what about like the computer industry with aerospace engineering? We know like computers and aerospace engineers blend well. Even during in the 60s and 70s, the machines that got the man to the moon and into the space for the first time had computers, though they were hardly as powerful as fast as the ones we use now. For example, the computer behind the guidance system of the Apollo missions had just 32 KB of memory and 4 KB of RAM, famously like less than the memory of a graphing calculator. Now, aeroplanes and spaceships have incredibly advanced systems that need computer programmers and software designers to create them. There are computerized flight simulator systems that requires the same. Without computing power, software, and the computer industry, the planes, helicopters, and rockets just wouldn't go at all. So, coming to the main important thing, the transportation industry, as I discussed earlier, it is one of the prominent thing, the speedy transportation of travelers, and shortly the launch of first adventurous space tourists. So there is a plenty of room in the transportation industry for aerospace engineers, including positions at the US Department of Transit or the FAA, the Federal Aviation Administration. So did you tell much about the travel industries where we'll discuss? That is all about like aerospace engineers are still needed to do well in this established travel industry to keep improving. And also when it comes to aerospace engineering and defense industry, the main concept of adaptation of this aerospace, there are numerous positions in the defense industry for aerospace engineers. Keep in mind that many of these positions require an official security clearance, so keep your record clean and stay out of trouble. Aerospace engineers in defense not only design innovative and experimental aircrafts, but also work on missiles and other important facets of defense. While some disagree with the increase in military spending over recent years, it has done a lot of good for the defense industry, which grew by almost 40,000 jobs in 2016, and the trend is like projected to continue. So the perks, as I like reflect my experience with Northrop Grumman, as reflected perks of being an aerospace engineer, the field of aerospace engineer has many perks besides working on innovative technology, and most full-time positions offer employee benefits like health, dental, and vision insurance, like paid time off, sick time, other perks of working for a greater employer. So what does like a top aerospace companies look for or offer to be? So there are many aerospace companies to choose from when you decide to become an aerospace engineer. You must be already aware of a few newer and innovative companies who are facing the great mystery of space tourism and exploration head on. And Blue Origin, SpaceX, and Virgin Galactic, as I told you earlier, many established like earthbound companies are also excellent options. And Boeing is an established aeroplane manufacturer, as I have much uh, kind of closer relation with Boeing Industries. Many commercial jets bearing the Boeing name, and is considered to be the largest aerospace company by some metrics, over like $86 billion of revenue each year. And Airbus is the second largest aerospace company, which I'm not much familiar with close to the engines, but the company is based on the metrics of revenue. They are known like facts for their giant Airbus 380 model capable of taking over 800 passengers on a single flight if a single class layout is used completely on board. Airbus has offices on every continent except Antarctica, of course. And the biggest aerospace manufacturers, when it comes to like United States, is often listed as the third biggest manufacturer of aerospace technology. And their aerospace manufacturing company, Pratt and Whitney, has been influencing the field of air flight since 1925, I believe. They design and manufacture military and commercial plane engines, and their engines are used in 25% of all commercial flights in the world. Similarly, when it comes to the best industries, there are like various industries, travel, defense, which I discussed earlier. So they're all like producing huge number of jobs or careers in various research fields of engineering. And coming to the main important thing, so how does this particular aerospace engineering jobs in the worldwide or in USA announce? So it is growing like at a rate of 6% by 2026 from the recent studies, I believe. And even Los Angeles, Wichita, and the area outside Orlando, where Cape Canaveral is located, also have a high concentration of aerospace engineers positions. There are almost 70,000 aerospace positions total in the USA. And like rest in the world, Canada, Europe, Asia, so that is like Australia, Russia, and everywhere, like it's growing like tremendous thing. So let me straight away like little more focusing on Boeing, how they are bringing it up. Boeing is like one of the top aircraft companies in the world. They have offices in 70 countries worldwide. It is one of the largest global employers of aerospace employees, with over 1,58,000 on their roster, I believe. And there is much more to like the important work they do with the NASA. Any aerospace engineer can likely find a niche that fits their interests. And coming to the associations, they have like all aerospace industry associations, the vertical flight societies, and there are many more like American Astronautical Societies, and Association for Unmanned Vehicle Systems Innovations, and perks of working at NASA as an aerospace engineer. And coming to the perks, NASA is one of the best places to work in the field of aerospace engineering. So kids dream of working for NASA, and adults do too. A small number of them actually get to live out their dreams. The major benefits to work with NASA. And coming to one of the like the salary perks, I don't need, I mean, I don't want to discuss, but everyone looks at those perks. Around 80,000 USD per month as a beginner that you can earn being an aerospace engineer at international standards. And coming to the next concept, like the main core one, the aerospace materials, that is what like today we are going to discuss. And I am going to like touch on past, present, and future of aerospace materials. Constant pressure for greater fuel efficiency is forcing aerospace manufacturers to find ways to incorporate new and existing materials that had once been considered impractical to machine. So something like 40 years ago, aluminum dominated the aerospace industry as the new kid on the block. It was considered to be lightweight, inexpensive, and state of the art. In fact, as much as 70% of an aircraft was once made of aluminum. Other new materials such as like composites and alloys were used, including titanium, graphite, fiberglass, but only in very small quantities, 3% here or 7% there. Readily available aluminum was used everywhere, from the fuselage to main engine components. Times have changed. A typical jet build today is as little as 20% pure aluminum. Most of the non-critical structural materials, paneling and aesthetic interiors, now consists of even lightweight carbon fiber reinforced polymers, we call CFRPs, and honeycomb materials. Meanwhile, the engine parts are critical components. There is a simultaneous push for lower weights and higher temperature resistance for better fuel efficiency, bringing new or previously impractical to machine metals into the aerospace material mix. And coming to the aerospace unique among these industries in terms of materials, aerospace manufacturing is unique among other volume manufacturing sectors. And this is especially true of aerospace engine manufacturing. The engine is the most complex element of an aircraft, houses the most individual components, and ultimately determines fuel efficiency. The advent of lean burn engines with the temperature potentials as high as 3,800 degrees Fahrenheit and something like 2,100 degrees centigrade has helped drive demand for these new materials. Considering that the melting point of current superalloys is around 1,850 degrees centigrade, the challenge becomes finding materials that will withstand hotter temperatures. To meet these temperature demands, heat-resistant superalloys (HRACs), including titanium alloys, nickel alloys, and some non-metal composite materials such as ceramics, are now being brought into the material equations. And these materials tend to be more difficult to machine than a traditional aluminium, historically meaning shorter tool life and less process security. There is also high process risk in machining aerospace parts because margins for error and non-existence at 35,000 feet cruising altitude. Tolerances in aerospace are more precise than almost any other industry. This level of precision takes time. The longer machines times are required for each component, and more time per part makes scrap relatively expensive when factoring in time investment. Also, compared to other industries, aerospace component orders often consist of short run quantities and long lead times, rendering scheduling for productivity, throughput, and profitability difficult. Unlikely any other industry, but oil and gas, which also has huge high temperatures, pressures, and corrosion requirements, aerospace materials themselves impact component design. Design for manufacturability, like DFM, is the engineering art of designing components with a balanced approach, taking into consideration both component function and its manufacturing requirements. This approach is being applied more than something like more in industry component design, because its components have to accomplish certain loads and temperature resistances, and some materials can only accommodate so much. Materials and component design truly drive one another as opposed to one following to the other. This give and take relationship between material and design is a particular consideration where investigating next generation materials. Aerospace manufacturers are a breed part of all these reasons. It's not surprising that their assortment for material is unique. Coming to the new material landscape, this I'll discuss once I'll go with the latest materials that are being done. So coming to the materials and the aerospace industry. So before going to that, we need to discuss few questions to consider for enhancing innovation and competitiveness. Something like expanded federal investments in research and education and the impact, acceleration of ROI in basic research, collaboration models for research, and the specific areas of fundamental research and workforce challenges. So for all these questions, when we get to discuss, we need to discuss a little more on Boeing products, how they increase. So coming to the Boeing products, they have two main concepts: the commercial airplane family and the integrated defense systems. So coming to the commercial airplane family, they have right from 737 to 787, which is nothing but Dreamliner, and the integrated defense system, something where it has F-18 to Homeland Security, Delta, Apache, and tankers, and even satellites. UAVs are unmanned air vehicles, they are also in the manufacturing. So coming to the materials research in the 21st century defense, the revolutionary capabilities from R&D in structural and multifunctional materials, energy and power materials, electronic and photonic materials, functional organic and hybrid materials, bio-derived and bio-inspired materials. So coming to a few recommendations that can be made: accelerate materials transition from concept to service, computational modeling, integrate research in various material classes, and discover materials with sustainability improvement properties, and material research from conception to service retirement. So where we can see the strength and corrosion resistance improvements related to 7075 and T65 and new 7 series alloys. So we had a leap curve in here where we'll consider the low, medium, and high corrosion resistances. So always thin products are less than 75 mm and thick products are between 75 to 200 mm, where we consider when it comes to alloys in aerospace. Coming to the composition weight percentages, so these are the few compositions where we'll consider the zinc is being used in more in 7 series alloys. So compared to the other elements where it is leading like 8 in 7055, 8% weight, and the same manganese and copper. So these are the few compositions, weight compositions of 7 series alloys. So when it comes to the industry perspective, we have to discuss a few things on it. Technology is fuel growth, something like the products 787 Dreamliner, as I discussed with you, with the Boeing product, and the services expand the value of product to customer. Technologies reduce the bottom line. Design enables more efficient structures, and coming to manufacturing enables streamlined production. The breakthrough technology is something what will the future bring, and fundamental research, what are the gaps and what is needed to close them. And similarly, workforce challenges, as we discussed earlier in it. So coming to the growth, new technologies that enable new products and services. So we will come across these things, the large scale composite components and advanced manufacturing process, system health monitoring, next generation engines, more electric power systems, and enabling interior architecture, integrated avionics, advanced flight controls, wireless IFE, and other technologies to improve the cabin, noise reduction technologies, advanced recycling technologies for airplanes. So there are many more to discuss about this 787 Dreamliner. So when you see this particular Dreamliner, it has like the best introduction of the present era, that we can say. Like in the earlier one, I'm saying like 787 has the better futures compared to the other competitors in the market. So what made it special is all about its composites that can used in it. Coming to the composite serves as 787 primarily structural materials. So where we can see like the 50% is of like composites, and the titanium that made main role, aluminum is as well we are discussing. So I told you earlier, right from one piece forward fuselage to the test wing and the engine. So all we consider is like these main concepts. The lighter it should be, the more durable it has to be, and the reduced corrosion and fatigue and reduced scheduled maintenances, and it is always open to new design possibilities. And similarly, the future of this composites enabling high rate of production. So when we discuss like the world fleet, it might grow up like tremendously. We can see it in here as the days been passing on. Like we are going with more amount of titanium and more amount of composites, wherein the concept of like Boeing products. As I told you earlier, I'm discussing only with Boeing products as I'm very much familiar with that. So what we can see in here, the continued development of advanced composites will be required to affordability satisfy high rate production needs. So that is the main important concept that we'll look. So coming to the titanium usage in aircrafts has been increasing day by day. So as the years roll out, so it is continued development of like improved alloys are needed to improve performance, manufacturability, and affordability as well. So as we can see like here, the growth of this particular titanium, as composites are always driving growth in titanium. So the main characteristics, when it comes, we have to discuss these characteristics. So the first one is like extreme affordability, which is nothing but like cost improvements of factors from 2 to 100, and universally friendly, minimal to no environment impact of product throughout its full life cycle. And coming to network centric, multiple assets that collaborate on a network to optimize the system performance. And the last, I mean, the most important one, the superhuman intelligence, platforms and systems with design making compatibilities better than human. And similarly, the other three, highly integrated. It is nothing but like integration of many functions into a single component, and breakthrough performance, which is nothing but 2 to 100 fold performance improvements, adaptability to change. It is easy to upgrade with the latest technologies advancements. So coming to the new technologies, like the growth, new technologies that enables new products and services, which we have to like more focus when it coming to the research. So the first important thing is like product support. Integrated vehicle health management is the present trend in any industry that is taking a new era of research that has to happen. So coming to the develop diagnostic or prognostic technologies that will allow us to monitor the performance of our products in the field to ensure optimum performance and maximum availability to our customers. So when we can see here, the system integration is a combination, like where we can see like the monitoring of these products and detections, the fault detections or any kind of occurrences that can happen. This can be achieved through integrated vehicle health management. And similarly, analyze and plan as a cumulative decision support. And similarly, manage nothing but the maintenance management. And the last but not least, the maintenance mods and repairs that we are going to do. So this indicates like the developed advanced technologies which will improve the quality and reduce the cost of maintenance and modifications and even repairs as well. So when it comes to a broad and detailed discussion about product improvements, design technologies, enabling more efficient structures, we always discuss about low cost and lower weights. So develop innovative structural concepts which will be high, I mean lighter, easier to build and maintain, and costless to fabricate and support. Something like fewer parts, fewer fasteners, less assembly, and lower cost is always the task that can be discussed through. And even the design and analysis tool develop the necessary analysis compatibilities needed to support the advanced concepts and integrate those into common design tools and processes. Something where we can see like faster designs, more iterations, or something of similar concepts. And coming to the materials by design, create high performance materials and leverage with the design concepts to improve performance and or lower costs. So where we can say like materials by trial and error, lots of testing, architect the materials necessary to enable higher performance designs. So similarly, like we know how we can grow in that. Coming to the concept of modeling and simulation, it is nothing but develop, design, and build multiple variations like iterations virtually to reduce costs and speed developments. So here, like we can see the physical and the virtual environments where we are developing. So the virtual environment is almost likely to have the physical environment. So this is the achievement that we can do with any industries. So this is one of the example that have been across with Boeing in Turkey. So coming to the similar one, when it comes to analytical techniques replacing empirical testing, this is nothing but develop methods to verify and clarify new structural concepts and materials forms to speed those advancements and product lines. So that is very insertion, like how we can see the time to insertion readiness, and the time to insertion readiness is like reduced by 55%. So the traditional methods here we can see where the traditional test supported by analysis, and the goal analysis supported by experience and test demo. So this indicates the test demo in the lower side, and the upper side it indicates the support to analysis. And coming to the network enabled manufacturing, so it is one of the trend. The technologies enable lower cost structures, develop often architecture models for linking system of systems. Example, indoor GPS, RFID, smart tools, laser production, all linked to manufacturing work instructions and quality management systems. And nowadays, like NEM converts today's aerospace factories where information collection and diagnostics are mostly manual to state of the art automated information database resources like in real time. This methodology is well adapted to the future engineering workforce who are familiar with intelligent computerized systems. Similarly, when it comes to aerospace direction, increased global sourcing of subcomponents and materials, global sourcing of assemblies, Airbus to assemble plants in China, and networked manufacturing, materials by design and lean manufacturing, green materials and process, networked aircrafts and satellites, etc. And coming to the aerospace workplace needs, when we are designing or modeling it, it mainly needs like educated scientists and engineers, globally sourced, clearable for defense-related projects, mathematical and analytical capability, something like probability and statistics, communications across various disciplines, not just interdisciplinary studies, but interaction. So Boeing invests significantly in employees training, both in-house and at university levels as well. Coming to the fundamental research gaps and needs that we can identify in these materials or the advancement in materials, the main important concept is like modeling and simulation. Material informatics, like which comes under modeling, and simulation of manufacturing process, multifunctional materials, lower cost and affordable replacement for strategic materials, self-assembled structures, something like grow for parts, in-service assessments of the health of materials, something like diagnostics and prognostics, which I was discussing earlier. Always like take it something into the mind. Materials are key to maintaining competitiveness. Every day they are growing like anything in the current industries. So when it comes like, as I told you earlier, I'm going to a little bit discuss on the new material landscapes. So that is the main important theme of this particular FDP. Standard aerospace aluminum, something like 6061, 7050, and 7075. And traditional aerospace materials, nickel 718, titanium 6A, I4V, and stainless 15 5ph, I guess, still have applications in aerospace. These metals, however, are currently ceding like territory to new alloys designed to improve cost and performance. To be clear, these are the new materials, aren't always new. Some having been able to decades. like rather they are new to practical production applications as machine tools and tooling technologies and insert coatings have sufficiently advanced to tackle difficult to machine alloys. Even though the amount of aluminum is declining in aircraft, its use is not completely disappearing. In fact, aluminum is coming back, especially in cases where the move to CFRP, excuse me, as I told you earlier, has been cost prohibitive or unsuccessful. But the reappearing aluminum is not your father's aluminum. Titanium aluminide like TiL and aluminum lithium ALI, and for example, which have been around since 1970s, I believe, have only been gaining traction in aerospace since the turn of the century. Similarly to nickel alloys, in its heat resisting properties, titanium aluminum alloys retaining strength, corrosion resistance in temperatures up to 600 degrees centigrade, but these are more easily machined, exhibiting similar machinability characteristics to alpha beta titanium, such as Ti6Al4V, I believe. Perhaps more importantly, these elements has the potential to improve the thrust to weight ratio in aircraft engineers because it's only half the weight of nickel alloys. Case in point, both low pressure turbine blades and high pressure compressor blades, traditionally made of dense nickel based super alloys, are now being machined from titanium alloy, like aluminum based alloys. General Analytics GE was pioneer in this development and uses titanium aluminum low pressure turbine blades on its GE NX engine, I guess. The first large scale use of these material in a commercial jet engine in this case is like a Boeing 787 Dreamliner, which I have shown you earlier. Another reintroduction of aluminum to aerospace is found in weight saving aluminum lithium, and specifically designed to improve properties of 7050 and 7075 aluminum. Overall, the addition of lithium strengthens aluminum at lower density and weight, two catalysts of aerospace material evolution. Aluminum lithium alloys, high strength, low density, high stiffness, damage tolerance, corrosion resistance, and even wheel friendly nature makes it a better choice than traditional aluminums in commercial jetliner airframes. Airbus is currently using AA2050. Meanwhile, Alcoa is using AA2090 T83 and 2099 T8E67. You can Google it otherwise. The alloy can also be found in the fuel and oxidizer tanks in the SpaceX Falcon 9 launch vehicle. And it is used extensively in NASA rockets and shuttle projects. Sometimes, like titanium 5553 is another metal that is reasonably new to aerospace, exhibiting high strength, lightweight, and good corrosion resistance. Major structural components that needs to be stronger and lighter than previously used stainless steel alloys are perfect application points for this titanium alloys in comparison. And nickname 5553. This has been a notoriously difficult material to measure until recently. It was difficult. Maybe in future, like we can grow up some more materials where these materials can be easily machined and that can be implemented. And extensive research and development has been devoted to making the metal practical to machine. And 5553 has recently proven to be very aforementioned, as I told you earlier. But once an operator has a poor parameter set, 5553 machine predictably won't be like a good outcome of it. The key with 5553 is to run a bit slower and optimize the tool path and coolant system to achieve a good balance of tool life and tool security. Some structural pieces like fasteners, landing gears, and actuators, which requires raw strength with lightweight properties, being less of a priority. In such cases like Carpenter Technologies, Ferrium S53 steel alloy has provided mechanical factors equal to or better than conventional ultra high strength steels such as 300M and SAE 4340. I'm not that good at numbers, excuse me, with the added benefit of general corrosion resistance. This can eliminate the need of for cadmium coating and the subsequent related processings. So coming to the composites hit their stride. It is very similar. Like composite materials also represent a growing piece of the aerospace material pie. They reduce weight and increase fuel efficiency while being easy to handle, design, shape, and repair and maintain even. Once like only considered for light structural pieces or cabin components, composite aerospace applications range now just into like true functional components, wings, fuselage skins, engines, and landing gears, etc. Also important like composite components can be formed into complex shape that for metallic parts would require machining and creating joints. Preformed composite components aren't just lightweight and strong. They reduce the number of heavy fasteners and joints, which are like potential failure points within an aircraft. In doing so, the composite materials are help to drive an industry-wide trend of fewer components and overall assemblies using one-piece designer wherever if it is possible. While CFRPs represent the lion's share of composite materials in both cabin and functional components, the honeycomb materials provide effective and lightweight internal structural components. So next generation materials include ceramic matrix composite CMCs, which are emerging in practical use after decades of testing. CMCs are comprised of ceramic matrix reinforced by a refractory fiber such as silicon carbide fiber. They also offer low density weight and high hardness, and most importantly, superior thermal and chemical resistances. Like CFRPs, they can be molded to certain shapes without any extra machining, making them ideal for internal aerospace engine components, exhaust systems, and other hot zone structures, even replacing the latest in HRSC metals listed earlier. New materials that address like in aerospace industry in current days are something like metallic and composite materials like continue to be developed and improved to offer ever increasing performance, whether that's a lighter weight, greater strength, or better heat and corrosion resistance. Accelerating this evolution of new materials, advancements in machining and cutting technologies give manufacturers unprecedented access to the materials previously deemed impractical or too difficult to machine. New materials adoption is happening exceptionally quickly in aerospace, requiring DFM-minded interaction between material characterization and component design. The two must be in balance, and one can't really exist outside of the context of the other. Meanwhile, one-piece designs are continuing to reduce the number of components in overall assemblies. In general, this bodes well for the composites and aerospace, which can be formed instead of machined. A variation of this trend exists in metallic structures as more components are conditioned in forgings to get the near net shape, reducing the amount of machining. Elephant skins, roughened shapes, and thin floor sections all reduced materials cost and the total number of components, but setup and fixturing continue to be challenges. Also something like but designers and machinists, engineers, and machine tool cutting tool partners are developing new solutions to keep the evolution churning forward. The mix of materials in aerospace will continue to change in coming years with composites, freshly machinable metals, and new metals increasingly occupying the space of traditional materials. The industry continues to march towards components of lighter weights, increased strength, as I told you earlier, with the greater heat and corrosion resistance. The component count will decrease in favor of stronger near net shapes, and design will continue its close collaboration with material characteristics. However, we can say like the machine tool builders and cutting tool manufacturers will continue to develop tools to make currently unviable materials machinable and even practical. Uh, and it's done in the name of reducing the cost of aerospace manufacturer, improving fuel economy through efficiency and lightweight, and making air travel a more cost-effective means of transportation. So I hope I made it very clear with my presentation. So if anyone are having any doubts, so I am open for your questions. And thank you so much for the patience listening. So any questions? So always you can leave your questions in the live comment box. So I'm ready to address them. So fine, I have given my email ID over here and my contact number. So if you have any doubts in future, you can just dial me or write me. So I'm very much happy to reply you in this. So thank you so much for the patient listening. So have a wonderful day, and I thank IASC, International Association of Academic Plus Corporate, for establishing this platform at an international level where all the fraternity of engineering can avail this great future, the recent advancements that is happening that can be taking into consideration. I think I have a question. Why this manganese is not preferable? Manganese metabolism and its disorder is one of the reasons. There is no readily available and easy methods to assess magnesium, like magnesium status, acid based disturbances. There are a lot more metabolism and its disorders that we have to consider. And when it comes to the absorption of magnesium, one study found that very high doses of zinc from supplements can interfere with magnesium absorption and disturb the magnesium balance in the body also. So that might be the one of the reason why they are not choosing it over aluminum. And the next one is like which we can use it for aerospace structures. There are different materials. The trend in aeronautical structures or aerospace structures, from all metal constructions to composites. Coming to the manufacturing methods for these are traditional methods like processing methods within these molding categories, and each of its own benefits. Like the type of structure that needs to be developed requires an additional thing. Coming to main important thing, two materials play a major roles in the modern aerospace, like aluminum alloys for airframes and skins, and composites for structures. So thank you. If you have any further questions, you can always write me to my mail ID. So thank you so much, IASC, for creating this platform for all the researchers and current trends and research in aerospace and even the material advancements. Thank you so much.